The P-38 Lightning returned to Hollandia with fuel gauges reading 0. Not low, 0. Ground crews who serviced the fighters after long-range missions in mid-1944 had stopped being surprised when pilots climbed out of cockpits after 7-hour flights with no measurable fuel remaining in their tanks. The mathematics were straightforward. A mission to targets north of New Guinea's coast required 1,100 miles of flying. The Lightning carried 410 gallons internally. Standard cruise procedures consumed fuel at rates that left nothing for weather diversions, nothing for extended combat, and nothing for error. Fighter Command had accepted this as the operational ceiling. The P-38's range was what it was. Allison published performance charts. Lockheed provided operating manuals. Army Air Force's training programs taught specific power settings. Pilots learned to cruise at 2,200 RPM, with mixture controls set to auto-rich. These settings kept cylinder head temperatures within safe limits and prevented detonation. They also consumed approximately 100 gallons per hour from both engines combined. Every pilot understood that reducing RPM below 1,800 while maintaining manifold pressure above that figure would create an oversquare condition. Oversquare operation caused detonation. Detonation destroyed engines. Losses from fuel exhaustion were increasing. Squadrons based at forward strips in Dutch New Guinea launched strikes against Japanese positions on Biak, Noem4, and along the Vogelkop Peninsula. Weather patterns across the region were unpredictable. Tropical storms formed without warning. Cloud layers dropped to deck level. Pilots who encountered weather between target and home base had two choices: divert to alternate airfields that might not exist, or continue home and accept that they would run dry before reaching the coast. Between April and June 1944, 5th Air Force lost 11 P-38s to fuel exhaustion when weather forced route deviations. None of those aircraft were damaged by enemy action. Their engines functioned normally until fuel starvation stopped them. The operational problem was becoming a strategic constraint. MacArthur's advance toward the Philippines required air superiority over ever longer distances. Each island captured provided a new airfield, but the pace of advance was limited by how far fighters could reach from existing bases. If the P-38's radius remained fixed at 570 miles, certain targets would remain inaccessible until amphibious forces seized closer territory. This meant slower progress, more casualties in ground assaults, and extended timelines for operations that depended on eliminating Japanese air power before invasion forces arrived. Fighter groups submitted requests for additional drop tanks. Production facilities were already manufacturing external tanks as fast as metallurgical resources allowed. Adding capacity would divert aluminum from bomber production. The requests went unanswered. Groups experimented with reducing ammunition loads to save weight. This created different problems. Pilots who encountered multiple targets ran out of ammunition before running out of fuel. The weight savings were marginal anyway. A full ammunition load for one P-38 weighed 490 pounds. Removing half the rounds saved 245 pounds, which translated to perhaps 15 additional miles of range. The mathematics did not solve the problem. Charles Lindbergh arrived at Hollandia on June 26, 1944, carrying authorization from 3rd Air Task Force that most squadron commanders found administratively questionable. He introduced himself as a technical representative from United Aircraft Corporation. He was not in uniform. He held no military rank. He was 42 years old. The younger pilots who controlled the Pacific Theater's most lethal fighter unit had little reason to trust that a civilian, whose fame came from flying alone across an ocean 17 years earlier, would understand formation tactics, air-to-air combat, or the operational realities of fighting Japan's remaining air forces. Lieutenant Colonel Charles MacDonald commanded the 475th Fighter Group. His unit had produced 10 aces. The group's 3 squadrons had recorded 147 confirmed aerial victories since activation 13 months earlier. MacDonald knew his pilots flew their aircraft to the edge of fuel capacity on every long-range mission. He also knew that expertise sometimes resided outside the military's institutional knowledge. When Lindbergh explained he had been studying P-38 fuel consumption patterns and believed he could extend the aircraft's range significantly, MacDonald did not dismiss the claim. He arranged for Lindbergh to fly a combat mission the following day. Performance in combat would determine whether the civilian's theoretical knowledge had practical value. The mission on June 27th targeted enemy positions along Geelvink Bay. Lindbergh flew as Blue 3 in a 4-ship element. The flight encountered moderate anti-aircraft fire. Lindbergh's formation discipline was precise. His gunnery was adequate. His aircraft returned with the formation. What the crew chief noticed after landing was that Lindbergh's P-38 had 210 gallons remaining after a flight lasting 6.5 hours. Other aircraft from the same mission landed with gauges showing 30 gallons or less. The discrepancy was too large to attribute to gauge error or individual fuel tank variations. MacDonald called a meeting 2 days later. The group's pilots gathered in their recreation facility, which consisted of palm fronds over packed earth, with a single ping-pong table. Lindbergh stood before men who had been flying P-38s in combat for over a year and explained that standard operating procedures were wrong. The cruise settings every pilot had been taught were inefficient. The fuel mixture they used was too rich. The engine RPM they maintained was too high. And the combination of power settings they had been specifically warned never to use was not only safe, but optimal for maximum range. He described specific numbers. Reduce engine speed from 2,200 RPM to 1,600 RPM. Increase manifold pressure to 30 inches of mercury. Set mixture controls to auto-lean instead of auto-rich. Maintain indicated airspeed at 185 miles per hour. These settings would reduce total fuel consumption to approximately 70 gallons per hour. The aircraft would cover the same distance in the same time, while burning 30% less fuel. The operational radius would increase from 570 miles to more than 750 miles. Missions that currently left no margin for error would conclude with 60-minute fuel reserves. The pilots understood immediately that Lindbergh was describing over-square operation. Manifold pressure of 30 inches with RPM at 1,600 created a ratio that training explicitly prohibited. The standard teaching was that manifold pressure should never exceed RPM by more than a few inches. Excessive pressure with insufficient RPM caused destructive detonation inside cylinders. Cylinder heads would overheat. Pistons would fail. Connecting rods would break. Catastrophic engine failure would occur, likely over water, likely beyond gliding range of land, resulting in loss of aircraft and pilot. Several pilots said this openly. The technique was dangerous. It contradicted established training. It would destroy engines. Lindbergh's response was that he had already flown multiple combat missions using exactly these settings. His engines showed no sign of damage. Cylinder head temperatures remained within normal operating ranges. Oil pressure stayed stable. The engines simply consumed less fuel because they were operating in their most efficient power band. The proof was not theoretical. It was documented in the fuel remaining in his tanks after every flight. The first pilots who tested Lindbergh's settings did so with the understanding that they might be gliding back to base on one engine. P-38 doctrine emphasized the twin-engine advantage over water. Lose one engine, and the remaining Allison could bring a pilot home. Lose both engines simultaneously, and the outcome was fixed. The initial test flights were short-range missions with alternate airfields available. Pilots kept one hand near the mixture controls ready to enrich fuel flow the moment cylinder head temperatures began climbing toward red line. The temperatures did not climb. At 1600 RPM, with 30 inches of manifold pressure and auto-lean mixture, the Allison V1710 engines ran cooler than at standard cruise settings. The lower RPM reduced mechanical friction. The leaner mixture eliminated excess fuel that had been used primarily for cooling at higher power outputs. What pilots noticed first was the sound. The engines at 1600 RPM produced a different tone than at 2200 RPM. The familiar deep rumble became something quieter, steadier, less aggressive. It sounded wrong. But the gauges showed it was functioning correctly. After 20 hours of test flights across multiple aircraft with no mechanical failures, McDonnell authorized squadron-wide adoption. The technique required precision in execution. Pilots had to synchronize both engines exactly. Any imbalance between left and right engine settings created asymmetric thrust that made formation flying difficult. The mixture controls needed adjustment based on altitude. At higher altitudes, the air was thinner, and the auto-lean setting had to be manually enriched slightly to prevent overly lean operation. Below 10,000 feet, auto-lean worked as Lindbergh described. Between 10,000 and 20,000 feet, pilots learned to advance the mixture controls 2 increments from full lean position. The fuel savings became apparent across the group's operational tempo. On July 8, the 475th escorted B-24 Liberators, striking Manokwari Airfield, a round-trip distance of 840 miles. Standard procedures would have required pilots to turn for home immediately after the bombing run concluded. Using Lindbergh's settings, the fighters remained over the target area for 20 additional minutes, conducting combat air patrol while the bombers reformed. All aircraft returned with fuel reserves exceeding 45 minutes of flight time. No emergency landings occurred. No aircraft diverted to alternate fields. The mission that would have been marginal under old procedures had become routine. 5th Air Force Headquarters received the 475th's fuel consumption reports in mid-July. The data showed consistent reductions across all long-range missions. Other P-38 groups requested details. The 49th Fighter Group, operating from the same base complex at Hollandia, sent pilots to observe the 475th's procedures. The 8th Fighter Group dispatched its operations officer to interview Lindbergh directly. By late July, P-38 squadrons across New Guinea were experimenting with variations of the technique. Some units found that 1,650 RPM worked better than 1,600 for their specific aircraft. Others adjusted manifold pressure to 28 inches instead of 30. The core principle remained identical: lower RPM, higher manifold pressure, leaner mixture. What emerged was not a single prescribed setting, but a methodology. Lindbergh explained the physics to pilots who asked technical questions. Aircraft engines produced power by converting fuel into expanding gases that drove pistons. Efficiency was the ratio of power output to fuel consumed. At high RPM, engines cycled rapidly, but wasted energy on mechanical friction and used excess fuel for cooling rather than combustion. At lower RPM, with adequate manifold pressure, the same power output required fewer combustion cycles. Each cycle burned fuel more completely because the leaner mixture provided just enough fuel for stoichiometric combustion without excess. The key insight was that oversquare operation was only dangerous at high absolute power outputs. Taking off with 60 inches of manifold pressure at 1600 RPM would destroy an engine in seconds. But cruising at 30 inches and 1600 RPM was moderate power operation. The ratio was over square, but the actual stress on engine components was lower than at 2200 RPM. The lower rotational speed reduced bearing loads, decreased vibration, and minimized thermal stress. What had been taught as dangerous was actually a more efficient operating regime that reduced wear while extending range. The operational implications ahead across multiple mission types. Long-range fighter sweeps that had been canceled due to fuel constraints became viable. On July 19th, the 475th conducted a sweep to Manokwari and continued north to Sorong, a total distance exceeding 900 miles. The fighters engaged Japanese aircraft over Sorong, expending ammunition in a combat lasting 12 minutes, then returned to Hollandia. Flight time exceeded 8 hours. All aircraft landed with measurable fuel remaining. Under previous operating procedures, the mission profile would have been impossible. Bomber escort missions changed character. B-24 formations, striking targets in the Halmahera Island group, required fighter escort across 650 miles of ocean. Standard doctrine called for fighters to escort bombers to the target, remain overhead during the bombing run, then depart immediately for home. Fuel margins left no room for extended combat. If Japanese fighters appeared after the escort departed, bombers faced interception without friendly fighter cover. Using extended-range cruise techniques, P-38s could escort bombers to target, maintain patrol overhead for 30 additional minutes after bombing concluded, then escort the formation partway home before fuel required breaking off. Japanese air losses in the Halmahera area increased measurably. Between August 1st and August 15th, 1944, 5th Air Force P-38 units claimed 43 aerial victories in combat around Morotai and Halmahera. The previous month had seen 18 claims in the same area. The increase correlated directly with fighters' ability to remain in the combat area longer. Japanese pilots who had learned to avoid engaging American fighters near the target, knowing the P-38s would depart quickly due to fuel concerns, now encountered fighters that remained overhead for extended periods. The technique also reduced non-combat losses significantly. Weather over New Guinea was characterized by rapid storm development. Pilots who departed on missions during clear conditions often returned to find their home base obscured by thunderstorms with cloud tops above 30,000 feet. Diverting around weather required fuel. Under tight fuel margins, pilots attempting to circumnavigate storms sometimes ran dry before finding clear air. Between April and July 1944, 11 P-38s were lost to fuel exhaustion. Between August and October, after extended range techniques became standard practice, 2 P-38s were lost to fuel exhaustion, both due to combat damage that caused increased fuel consumption rather than weather-related diversions. 5th Air Force published updated cruise control guidance for all P-38 units in September 1944. The document codified Lindbergh's technique with specific power setting tables for different altitudes and mission profiles. Pilot training syllabi were revised to include instruction on lean-of-peak mixture operation. The institutional resistance that had initially met Lindbergh's recommendations dissolved in the face of operational results. Groups that adopted the technique reported range extensions. Groups that delayed adoption saw no corresponding improvement. The correlation was direct. The strategic impact became visible in September and October as MacArthur's forces prepared for operations in the Philippines. Air superiority over Leyte required neutralizing Japanese air bases throughout the southern Philippines and the Celebes. P-38 groups based at Morotai could reach targets on Mindanao using extended-range cruise. These targets had previously been beyond effective fighter range. Bombers striking those positions had operated without fighter escort, accepting higher losses. With P-38s able to escort the strikes, bomber loss rates decreased, while mission effectiveness increased. The ability to reach 750 miles from base instead of 570 miles translated directly into which operations were feasible and which required additional intermediate bases. The mathematics were specific. Capturing an island to build an intermediate airfield required amphibious assault, ground combat to secure the position, construction of runway facilities, and establishment of logistics to supply the base. This process typically required 4 to 6 weeks and cost casualties proportional to the strength of Japanese defenses. If fighters could reach an additional 180 miles from existing bases, certain intermediate positions became unnecessary. The operations to capture those positions could be bypassed entirely. The timeline for reaching the Philippines compressed by weeks because strategic targets came within fighter range sooner. 3. Subsection 5. The technique's adoption revealed underlying assumptions about how military organizations validate knowledge. Training doctrine had established power settings based on engine manufacturer specifications and flight test data conducted under controlled conditions. These specifications prioritized engine longevity and mechanical reliability over maximum efficiency. Conservative power settings ensured engines would survive for their planned operational lifespan without premature failure. The cost of this conservatism was reduced range, but that cost had been invisible because no alternative methodology existed for comparison. Lindbergh's approach originated from different priorities. His 1927 Atlantic crossing required maximizing range from a single engine with fixed fuel capacity. He had experimented systematically with every possible combination of power settings during the flight, monitoring fuel consumption continuously, adjusting mixture and RPM based on observed results rather than published recommendations. The Wright Whirlwind engine that powered the Spirit of St. Louis had no published data for lean-of-peak operation during sustained cruise. Lindbergh developed that data empirically, in flight, with his life depending on the accuracy of his conclusions. The same methodology applied to the P-38 17 years later. Lindbergh did not trust manufacturer specifications over observed results. He tested combinations systematically. He measured fuel consumption directly. He monitored engine temperatures across multiple flights under varying conditions. When the data showed that lower RPM with higher manifold pressure produced better fuel economy without mechanical stress, he accepted the data, regardless of how it contradicted training doctrine. The validation came from measurement, not authority. Military institutions typically require extensive testing before changing operational procedures. New techniques undergo evaluation by test pilot units, analysis by engineering staff, review by safety boards, and approval through command channels. This process ensures changes are safe and effective, but it also means innovations take months or years to implement. Lindbergh's technique bypassed this process entirely. McDonald authorized adoption based on 2 weeks of squadron-level testing. Other group commanders followed after seeing the 475th's results. 5th Air Force formalized the change after 2 months of field use. The compressed timeline reflected operational urgency, but also demonstrated that validation could occur through combat results rather than institutional review. The civilian technical representative model proved effective beyond what anyone had anticipated. Lindbergh had been sent to observe P-38 operations and report findings to United Aircraft. He was not tasked with improving operational procedures. He held no authority to direct how military pilots flew their aircraft. But his specialized expertise in a narrow technical area, fuel management during long-range flight, matched precisely with a critical operational problem. The informal nature of his status allowed him to experiment and teach without navigating military bureaucracy. Squadron commanders could choose to adopt his recommendations or ignore them based solely on demonstrated effectiveness. By October 1944, other civilian technical representatives were being assigned to combat units with similar mandates. Aircraft manufacturers sent specialists to observe how their products performed under combat conditions, and identify improvements. Engine companies deployed engineers to troubleshoot mechanical issues that appeared in theater but had not manifested during stateside testing. The boundary between military operations and civilian technical support became more permeable as commanders recognized that solving complex problems required expertise that existed outside the rank structure. The extended range also changed how pilots understood their aircraft's capabilities. Before Lindbergh's techniques became standard, pilots treated published specifications as fixed limits. The P-38 had a certain range, a certain ceiling, a certain maximum speed. These figures were known quantities. After months of exceeding published range specifications routinely, pilots began questioning other limits. Could the aircraft climb higher than its rated ceiling under certain conditions? Could it exceed maximum speed in combat without structural failure? Were other published limitations equally conservative? Subsection 6. This questioning led to incremental discoveries across multiple performance parameters. Pilots found that the P-38 could sustain higher G-loads in turns than training had indicated, provided the maneuver was executed smoothly, without abrupt control inputs. The aircraft could safely dive at speeds exceeding its published red line if the dive was initiated from high altitude and recovery began before reaching dense air at lower altitudes. Maximum endurance with combat maneuvering was longer than calculated if pilots managed power settings carefully during the engagement. None of these discoveries were dramatic breakthroughs. Each represented small expansions of the operational envelope, accumulated through systematic testing by pilots who had learned that published limits were not absolute constraints. The cumulative effect was a force of fighter pilots who understood their aircraft more completely than training had taught them. They knew which published specifications were conservative estimates and which represented actual structural or mechanical limits. They understood how to operate near the edges of performance safely because they had explored those edges methodically. This knowledge base existed in the pilots rather than in manuals or doctrine. When new pilots joined squadrons, they learned through informal instruction from experienced pilots who demonstrated techniques that official training had not covered. Lindbergh departed the theater on August 12, 1944, after flying approximately 25 combat missions with P-38 units. His time in theater lasted less than 8 weeks. The techniques he introduced continued spreading across 5th Air Force, then to other theaters. By late 1944, P-38 units in the Mediterranean were using similar cruise settings. The 15th Air Force, operating from Italian bases, adopted extended-range procedures for escort missions deep into German-held territory. The technique that had been developed for Pacific Island hopping campaigns proved equally applicable to European strategic bombing operations. The final validation came from engine maintenance data. If Lindbergh's power settings actually stressed engines beyond safe limits, failures would appear in maintenance records after units accumulated flight hours using the technique. 5th Air Force maintenance officers compiled engine failure statistics for August through December 1944 and compared them to April through July data from before extended-range cruise became standard. Engine failure rates decreased slightly during the later period. The lower RPM operation actually reduced mechanical wear. Engines ran smoother with less vibration. Bearing surfaces experienced lower loads. The technique that had been predicted to destroy engines was extending their operational lifespan. Strategic planning for 1945 operations incorporated the extended range as a known capability. When targeting analysis was conducted for potential invasions of Formosa or the Japanese home islands, planners assumed P-38s would have 750-mile combat radius rather than 570 miles. This assumption changed which islands required capture for use as advanced air bases. It reduced the number of amphibious operations needed to establish air superiority over invasion beaches. The tactical innovation in fuel management became embedded in strategic calculations at theater and joint force levels. The P-38's role in the Pacific War's final year reflected these expanded capabilities. During the liberation of the Philippines, Lightnings based at Morotai and Leyte provided fighter cover over targets throughout the archipelago. During operations against Iwo Jima and Okinawa, P-38s from advanced bases flew extended patrols over invasion forces. The missions were feasible because range was no longer the limiting constraint. Pilots could reach distant targets, engage enemy aircraft when encountered, and return with fuel reserves adequate for weather diversions or mechanical issues. The operational flexibility this provided was measured in missions flown that would previously have been impossible. What Lindbergh contributed was not new technology. The P-38's engines, fuel system, and aerodynamics were identical before and after his arrival. The aircraft's physical capabilities had not changed. What changed was understanding of how to operate the aircraft within its existing capabilities. The knowledge was not complex. The power settings could be written on a card, small enough to fit in a flight suit pocket. But that knowledge, applied across hundreds of pilots, flying thousands of missions, extended American air power's reach by distances that changed strategic timelines and reduced casualties in operations that depended on air superiority. The story concluded without dramatic resolution because operational innovations do not have clear endpoints. The technique became standard procedure. Pilots who learned it taught others. The institutional knowledge base expanded to include information that had not existed previously. By war's end, extended-range cruise control for the P-38 was simply how the aircraft was flown. The innovation was no longer novel. It was routine. And in that routinization, the innovation achieved its full impact, not as a special technique for exceptional circumstances, but as normal procedure that every pilot executed on every mission without thinking it remarkable.